So we were talking about passwords and hashing and all the different mechanisms by which those two are kind of used in concert with each other, and then some of the kind of by design, by construction, by implementation weaknesses that have been found historically, and some of the inherent limitations of using passwords with regards to authentication. This topic is really meant to be about escalation, right? Which is from a certain amount of access that you've already obtained, how does one gain additional access? And we do differentiate between sort of the directionality of that additional access, which when you hear the term vertical access, that usually implies presumably kind of the default thought of gaining more escalatory access, which is you have some access on the machine, but it might be very limited. You might have gotten access through a service with very limited permissions on the resulting system. And can you gain additional access? Meaning perhaps you have a typical user account. Can you then gain a more administrative account access on that same machine? That is in contrast to something that's not technically really escalation, but just horizontal movement, either on the same machine or across multiple machines with the same kind of accounts and same kind of privileges here. Generally, we have a two-step kind of attack methodology. We have the initial vulnerability and exploit that's gaining us some sort of initial access, and we're effectively kind of bootstrapping from that and determining what else can we get. And this is the reason why even vulnerabilities, CVEs that by themselves seem to be relatively low severity, right? Maybe that numeric CVSS score is a relatively low number. If you're providing any sort of access to a system, there is then the potential for that kind of chaining of access from relatively limited unexpected access to then more privileged unexpected access. The two topics are complementary but also kind of orthogonal to each other, right? There are vulnerabilities that lead to gaining initial access. There are then separate vulnerabilities that lead to gaining additional access. And it turns out it's actually quite a bit more difficult to wipe out these nature of vulnerabilities, the ones that provide more vertical access. In theory, you unplug your machine, you turn off the potentially vulnerable service, you're not providing any remote access to that system. There is no initial access. But if you're assuming then by default there are legitimate users with legitimate access already to your system, or someone has already gained some access to your system, it turns out it's quite a bit more difficult to prevent that kind of vertical escalation type of connecting vulnerabilities together. We're already providing legitimate access. As these systems were initially designed, they really weren't considered very seriously about how do we prevent local users from acting maliciously on these machines. We've since been reimagining those considerations, but certainly initially by design, that was not a primary consideration. The thought was that people would be using the machine. We want to make sure they don't accidentally run into each other on the machine, but we weren't really building and designing things to prevent via that kind of exclusive access to resources. So everything we have now that tries to prevent vertical escalation is kind of an add-on. It's kind of a redesign. It's not as originally intended. I think for that reason, it's fundamentally a more challenging problem to prevent that gaining of additional access through some misconfiguration, through some vulnerability, given some initial access on the machine. One idea of example escalation just via misconfiguration, we were playing around a little bit with this in our current lab, is the idea of running sudo. Now, it should be sudo, should be sudo, call it whatever you want. Stands for super user do. So I would think it should be sudo, but here referred to as sudo all the time. It's a Linux utility that allows normal users to then execute code to kind of temporarily act as a super user. That's what the SU part of that stands for. It is something that can be configured that requires either a password be entered or have a password not be entered. And this is entirely a Linux issue here, consideration here. If that user account is the one you've gained access to, then via sort of intentional system design, then that user can then run either certain commands or potentially all commands as the super user on that system. That is related to the SU command, which is switch user, or you'll also hear it referred to as substitute user. And it's another Linux command utility that allows the user to open up a shell as another user. You can think of that as substitute or change user here. The root user is allowed to enter SU without entering a password, But if by default a user is given access to run substitute user with sudo commands, then that effectively allows your user to become root, allows your user to have all the potential permissions on the machine. That could be thought of as a misconfiguration, or it's intentionally by design, and it turns out you have to be very careful which users, which services you give the authority to kind of run commands with either super user do, or just be able to run the su command to change which user we have here. That is why you would see in a lot of the kind of things that we would typically run for like the low-level networking we've been doing, even like the ping command in some systems, oftentimes there's a distinction made between what can be running using kind of the traditional user-level networking stack in the system and what requires more sort of low-level access to the actual hardware in your system. Nmap is a good example of that. There's some default modes where it can just make use of user-level libraries, but for almost anything interesting you want to do with Nmap, you have to run it as root. You have to run it with those elevated permissions. So in theory, you want to run nmap on your system, and you have to run sudo first. You have to say super user do run nmap. Why have we not had to do that this semester? You've not had to run sudo at all for the most part outside of some Lab-05 configuration. Why have we not had to do that? We're logged in as root on the machine. Now that is pretty much still the typical kind of Kali Linux configuration. The expectation is anything interesting you want to do on Kali requires that low-level access, and so you just log in as root, and so you don't have to worry about doing those super user do things. That's kind of an issue in and of itself, though, right? There's something of a security vulnerability in being locally logged in as root on that machine. Whether that's best practice or not what we do in the lab, that's very common practice with installing and configuring a Kali box. But if you're not logged in as root and you want to do any of these low-level things, you need to have, presumably, access to that super user do. I don't mention it here on a slide, but the other thing that a lot of these kind of vulnerabilities and attacks we'll talk about take advantage of is if we have a utility or an application or a command that we want regular users to be able to access with effectively root permissions, with super user permissions, but we don't want them to have access to do things like this, we can tag the executable, tag the application or script itself with what's basically referred to as the super user bit. And if you ever look at the listing of a set of files and it's D, RWX, 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 or some things left blank, and you see an S there, that's what that S is referring to. It's saying regular users can now execute this particular application as if they were root, but just for this particular application without having to run super user. And generally is part of the source code for that application, certainly if it's written in C, there's a specific system call that's reserved for kind of temporarily giving access to root level permissions while executing that code. Those applications are necessary in modern Linux and Unix systems for things to run properly. They're also a kind of a guaranteed potential point of vulnerability and exploit for that reason, that because this application, and ping is a good example of that application, it needs low-level access to networking hardware to work. It has the super user bit set so that for that particular functionality, it can act as root just very temporarily. Consequently, if there's something that winds up being vulnerable with regards to the ping application itself, that is kind of an entry point for vertical escalation of the system. So when I talk about how it's fundamentally more difficult to kind of prevent, almost by design, vertical access in a system, and we have to be kind of constantly vigilant, and there's still constantly things that are being explored and discovered with regards to getting more vertical access in a system, and that nature of local escalatory vulnerabilities. It's almost by design. It's almost by design that we want at least temporarily people to have additional access just to be productive users of the system. Limiting it to only those specific guaranteed scenarios and not more general malicious scenarios turns out to be a very difficult thing to do, at least in practice. And of course, there's an XKCD comic for literally every single subtopic in this course, for better or for worse. I'll include them as necessary. They're also relatively easy to find. Here's an example of vertical escalation via a specific vulnerability. This is just one example, and it's one example that we're able to run in the lab. But again, we run it in the lab, and we just run a command line, and it works, and we don't really think too much about why it's working, and that's not a great use of our time. So in class, let's talk about why this particular vulnerability works. CVE 2016, 5195, and I'll open up the link here in the moment. more commonly known as dirty cow. It was around this era, and it's continuing today, that any interesting vulnerability has to have a snappy name, has to have its own like custom website to kind of market and broadcast the vulnerability itself. I don't know if that's a good trend, but that's definitely the trend, and it started a little bit before 2016, but it's still taking advantage today. It is currently old slash out of date. On a modern installed system or patch system today, this vulnerability would not work. But what's kind of interesting about it was the potential impact of it at the time, which is to say, the vulnerability was officially discovered in 2016. And whether this is simple or not in the CVSS scoring system, it's a little advanced in terms of our operating system knowledge, but in terms of like hacker parlance and categorization, it is a relatively simple exploit. It was considered to be vulnerable for nearly a decade before that, and they only just discovered that at the time. That's not a very common thing that occurs. What's a more common occurrence is some recent update, some recent new features, some recent patch created a vulnerability where there was not one before. So this one's kind of interesting in that here is the public disclosure of a particular vulnerability that allows for that vertical escalation. How long were people actually potentially taking advantage of it in practice? We don't actually know. And there's really no easy way of knowing that in these systems. So this is CVE 2016, and we now know a little bit more about how to read these CVEs. We can just kind of read a little bit about it. Race condition in a particular file in the Linux kernel through very many different versions of the Linux kernel allows local users to gain privileges. So that's a fancy just way of saying vertical escalation. If you're a local user, if you're gaining privileges, presumably the assumption is you can gain as many privileges then as you want, but allow local users to gain privileges by leveraging incorrect handling of a copy on write feature to a read-only memory mapping. We'll talk about what that means, but for now, the title, Dirty Cow, it's just a fancy, dirty copy on write. That's why it's called Dirty Cow. There's nothing bovine related to the actual vulnerability itself. It's kind of interesting that this is listed as only a 7.0 in the CVSS. We've talked about that. The one way to get up to those higher numbers in terms of vulnerability scoring is if it allows remote access to a system. So you could argue it's harder or more severe or more important to gain that initial remote access to the system. And then again, as I kind of mentioned, it's very hard to prevent that local vertical escalation. And so when it does happen, even if it's been happening for a decade and every single Linux system in the world was instantly vulnerable to it, it's still not considered necessarily that high in terms of the scoring of it. Someone already has presumably access or legitimate access to the system. Now they're going to overwrite the sudoers file and give themselves more access. Well, that's considered less in severity than just gaining that initial remote access in the first place. It takes advantage of a vulnerability class, right, our CWE, that has to do with race conditions. And this is not something that you don't necessarily even see even as you do a lot of programming, unless you were to do a lot of multi-threaded or parallel programming. And so what I mean by that is, depending on what courses you've taken and how far along you are in your own individual programs of study, oftentimes we're writing programs, we're really just thinking of like a single isolated task at a time. I have my function main or my entry point for my program, and my code's effectively executing line by line as it goes, running through loops, calling other functions, but it's kind of just the sequential kind of process where we go from start to finish in my program. And that's fine. That's a very common way to compose programs. This sequential programming model is a perfectly valid way of writing programs. Well, of course, in our system, we're not just running that one program, right? We ourselves are just launching the one, but in the system, there's dozens to hundreds to thousands of these threads that are running concurrently in our system to do all the other things that the system needs to do at any one given time, right? To run services, to manage resources, to just do all the other things beyond just running your particular program. Separately, there's a whole class of programming. You can just call it multi-threaded programming or parallel programming, where the concept is you as the programmer are not just writing this single kind of sequential program, because presumably there's some inherent parallelism in the task that you're executing. I don't want just to do A, then B, then C. I want to do A, B, and C while also in parallel doing X, Y, Z. And there's whole classes here at the university to learn how to do parallel programming. And if anything, it's gotten a lot easier in recent years than it was, 15, 20 years ago. But that's concurrent programming or parallel programming or multi-threaded programming. And it turns out, just in theory as well as in practice, that is a lot harder to do correctly. To write code and to use the libraries that we otherwise take for granted when writing code that allows two functions or two pieces of code to be accessing the same or similar resources at the same exact time. Ultimately, there's one processor executing your program at a given time. Maybe it's using multiple cores, but there's one resource using running your code at one given period of time. And so when we talk about a weakness or a vulnerability class referred to as a race condition, that's what it's generally referring to. The examples it gives in this document aren't super great in terms of explaining what's happening here. You really would want to take an operating system class first to really appreciate it. But the example they give in Perl is you have some code that is both checking how much balance is left in a bank account and also withdrawing some money from that bank account. If it's sequential code, life is pretty straightforward. Check if you have enough balance. If you do, withdraw the money. Otherwise, don't withdraw the money. And so this is example code that it's not, it's bad, but it's not necessarily the issue here. If it is then going to turn into some concurrent version of that same program where there's now two threads. One thread is checking balance, one thread is attempting to withdraw some money from that balance. Now you potentially, at least, and you can't look at the code and guarantee that's the case, but now you potentially have what's referred to as this race condition. Race, as in like a running race, a driving race, two threads trying to do something in parallel, and depending on how you write your program, you have little to no guarantees which one gets to its finish line first. And it turns out, if you're not careful, one getting there before the other one can lead to incorrect results as opposed to the other one getting there before the first one. And these things tend to be non-deterministic as well. It may work 999 times out of 1,000 that the correct thread gets completed first. We check the bank balance before we withdraw the amount. But if you do it enough times, it turns out that 1 out of those 1,000 times, again, this is processing speed, 1 out of 1 million times, 1 out of 1 billion times, it doesn't really matter. 1 out of a certain large number of times, our intention was to check the bank balance first before we withdrew money, but it just so happens that the withdrawing money code gets executed before the checking the bank balance code. That's not, to be honest, not the world's best example, because there's all sorts of pretty straightforward ways to prevent, overdrafting checks and making sure that things happen properly. There are whole programming paradigms that you may or may not have learned yet that have to do with concurrency and synchronization. Has anyone here used a mutex before in a program? Couple, good. That happens in at least a 3,000 level operating system class generally. You have to understand a little bit more of computer architecture to really know what's happening under the hood. But when you hear about semaphores and mutexes, you learn about them either in an operating systems class or potentially an algorithms class. And that's how we, in practice, try to maintain limited access to sort of concurrently shared resources in a system. They work. It just turns out, long story short, these things exist. They're actually a little hard to get correctly. And as a programmer, they turn out to be extremely hard to test that you've gotten them correctly. It's not as simple as just running the code and confirming that things are correct. We cannot guarantee, there's a little bit of non-determinism in a system. We cannot guarantee always the relative ordering of the code that we want to run in some particular order if they are launched concurrently. And so all sorts of bad things can happen due to race conditions. That is why it is a CWE of having concurrent execution using shared resources within proper synchronization, two threads going off in parallel. We always assumed one finished before two. Usually it happens, doesn't always happen. When they happen in the wrong order, bad things happen. My best attempt to explain what is happening in this code, and again, something that hamstrings it a little bit is, you don't have to be a C programmer to be in this class. And so I still think, though, You're not a C programmer. If you don't have those classes, that's fine. You have to have some programming background. You have to have some appreciation of what a program generally looks like. And so we get kind of the high-level gist of it. Whether we could understand it on a line-by-line basis is okay. This is kind of some advanced concepts anyway. And the syntax may look a little foreign to you, but we can walk our way through it and kind of gain a high-level appreciation of what is happening here. So this is our main. This is for the proof of concept. It's not exactly the one that you are running. It's quite close to the one that you are running in lab. It takes as argument a file that presumably is a protected file that only someone with those super user access should be able to overwrite content to. Might as well, I mean, there's a lot of options to really mess with stuff, but to give yourself write privileges where you only previously had read privileges, that sudoers file would be a good starting point. Just overwrite the sudoers file, add your own account to have full access to the machine, and this exploit then leads to effectively having easy full access to the machine here. That's what this version of the proof of concept exploit was doing. Give it the name, location of a target file, as well as what string, what new content I want to overwrite to the target file. We kind of just do that processing for you, so it just gives you a root shell, but you can use this functionality, this version to do it yourself as well. The idea of this copy on write, what would be the best way where it's listed here? This copy on write feature, it's a low-level operating system implementation detail. In Linux philosophy, every resource we want to access in the system is effectively a file, or at least a file descriptor. That is a design philosophy. It's not going to change anytime soon. As part of it, there's a hardware module on all modern architectures that's called a memory management unit, whose job is to do some very low-level checking of which threads have permissions to access which regions of memory. Bear with me here. There's like several semesters of content into that description, but that's effectively, there's a piece of hardware that we can control that takes care of tracking what region of memory is valid, what region of memory is not valid. If you've ever run a program that gave you a segmentation fault and crashed, that hardware unit was the root cause because you were doing something you weren't supposed to, the code was buggy, that unit detected that you tried to access memory that you weren't supposed to. The copy on write feature of a modern Linux operating system allows us to open up a file that we have read privileges to, allows us to map it to a region of memory. You'll see these calls to mmap, which is fundamental in memory allocation and management. And if we then choose to write to it, allows us to actually make a copy of that region in memory instead. So I open up a file. I have to have read permissions to open up that file in the first place. I then choose to write to that file. If I don't have proper permissions on that file, what the system will do for me will create a copy of that file and allow me to write to that copy of that file stored in memory. That is the copy on write semantics of how Linux manages file access and manages memory. There's not interesting technical reasons why that has to be the case, but because everything is effectively a file in Linux, if you want to be able to send a network packet, you have to have this copy on write feature inherent in the operating system. That is what the beginning of this code example is starting to set up in the beginning. So we just do some input parsing. We're going to have two concurrent threads. This is using pthread library here. We're going to open up our file that we want to eventually overwrite in read-only mode. We're then going to map that file to a region of memory. Don't worry about the actual syntax of this call. We're saying, here's a file. Give me the block of memory that can correspond to this file. And if you do this mapping with private, with a file read, it's going to have those copy on write semantics turned on for you. Technical, not that interesting so far. Then we're going to create our race condition. Create a new thread that's going to do something, and create another new thread that's going to do something else. So start your race. Two threads to do two different separate pieces of interesting work. As part of that thread creation syntax, there's the actual function we're going to call. So you can think of this as create a new thread starting from here that's going to call this function, with this input argument, the name of the file. Call now this function with the content we want to override in the file. That's what that syntax is doing. And then I think it's above here somewhere. We now have the actual functions for those two threads. They look a little weird. Any idea what this loop is doing? It's a weird looking loop, right? It looks like a bug, doesn't it? What is that for loop? Well, it's not running indefinitely, but it is running 100 million times, right? And I think there should be a similarly sized for loop in the other one as well, and there is. This is in a loop, basically spamming a function called memory advise. The one YouTube video that's linked here, he calls it madvise, but I think he's being silly. It's just memory advise. It doesn't stand for madvise. Memory advise. And we're actually basically spamming that call, if you want to think of it in those terms, over and over again, telling the operating system, hey, that memory I mapped, I don't need it anymore. Just delete it, just delete it, just delete it, just delete it. And the other thread is saying, hey, I'm sounding kind of casually here, I know, but hey, that region of memory that I'm interested in, and it's the same region of memory we're talking about, write this string to it, write this string to it, write this string to it, write this string to it. One thread is saying, delete it, delete it, delete it, delete it. The other one's saying, write this string to it, write this string to it, write this string to it, write this string to it. In a quote unquote correctly engineered underlying memory management part of the Linux kernel, every time you would request that I don't need it anymore, it'll handle that request. Anytime I request to write to it, it would just write to that copy. That is allowed. That's the copy on write semantics of memory management in this way. Just so it turns out, works the first time, works the second time, works the third time. Well, we tried 100 million times, and at some point amongst those 100 million times, they happen in the wrong order relative to each other. We put in this request for the delete. It does delete it. When we attempt to do the write to that copied memory region, that memory region is not there anymore, and this would be the bug. It falls back to writing to the original memory region, to the actual file itself. It's a subtle thing. As a programmer writing those functions, you never think someone would attempt to just do those two things in such, constant kind of, over and over again 100 million times. And I can't say for certain. We could probably test it to see where does it actually succeed. But we tried 100 million times. They're both doing those things effectively concurrently with each other. They're two separate threads. And eventually the ordering is just so right that it writes to that region of memory that it wasn't supposed to. And that's what that one line executable you're doing in that lab is doing. Launching two threads, just attempting over and over again. And because of this kind of well-known common weakness or vulnerability in software, it is hard to write multi-threaded software correctly. In this case, it mostly correct, and mostly correct was good for a whole decade until it was discovered that in fact it wasn't good enough and you had this ability to write to memory here. And there pretty much the game is up, I would say. How it actually then gets exploited in practice, once you're allowed to write to memory that you're not supposed to be allowed to write to, in Linux, everything is a file. Everything is going to eventually get mapped to some particular region of memory. Once you're allowed to access all of memory effectively, there's no shortage of things you can do. For our purposes, we change our user root, we get a root shell. Well, that's pretty good. That's good enough, right? But there was also, basically everything is possible once you have that level of access in a system. Just as the kind of final conclusory note on this topic of authentication and passwords, it's interesting that the recommendations for passwords have been, slowly changing over time. And so that the advice, the kind of standard advice, I think is still somewhat debatable, and there is no one solution for dealing with attackers who are trying to improve their access in a system. Advice number one, never using the same password for more than one account is pretty good advice. That was considered advice in the days of use of rainbow tables and reused hash values like we talked about, that if you're using the same password, there's a risk you have the same hash value, and consequently, without even needing to know your password, you may lose access to your password. Strong passwords, although what is a strong password is not sort of a scientifically proven thing. Complex passwords is a reasonable piece of advice. Longer passwords is generally an okay piece of advice, but longer is also not necessarily better. When we were talking about John the Ripper on Tuesday and talking about basically the default password cracking algorithm, um, it's able to be fairly clever, we saw, right? That it doesn't just try a dictionary, it starts with a massive dictionary potentially, and does all the kind of common permutations that we may have thought was clever a decade ago and now don't really add any additional security as well. I guess in terms of always use strong passwords, possible advice could be always use passwords that don't fall neatly into that algorithm and require sort of the brute force default backup plan of that algorithm, because the numbers are still in our favor there. You have a long enough password. If it's something that really only can be brute force, it's probably not going to be worth the effort. Don't use sticky notes. That's good advice as well. On systems that you are managing, try to the extent that it's possible to disable some of the older and well-known flawed authentication mechanisms in systems. That proves to be harder than it sounds. It sounds like good advice, but it's harder than it seems. Requiring multi-factor authentication, best practices in this field are obviously still not a stable thing, right? 5 years ago, it was considered to be the best practice to use text messaging, SMS, for your second factor in authentication. We still use that quite a bit today. It's been kind of provably shown that if someone really wants to access your account, MFA via text messaging is probably not going to be what limits them from doing so. Configuration-wise, protecting privileged or administrator accounts, that's something that certain systems will not do it all for you by default. Other systems will make that a relatively straightforward thing. And then when there is some data breach, again, this is also debatable advice, but if you read an article about data breach of an account that you had an account on, consider changing your password both for that as well as for other things that may have reused that password. There's other places that will advise using password managers. Does anyone here use a password manager? It's kind of hard not to today. You may use one and not realize you're using a password manager. Most web browsers will attempt to act as a password manager for you, and you have to keep constantly telling it, no, don't be my password manager. That's debatable advice as well. Hard to argue with the convenience factor of password manager. It helps with not reusing passwords. It can generate reasonably strong passwords. It kind of solves probably the sticky note issue with regards to passwords, but then potentially your password manager becomes a single point of failure as well. If you use a third-party system to store your password securely for you, and that third-party system is the one that suffers a data breach, then potentially you've given up the whole game at that point. The other advice, and lots of institutions require this, which is changing passwords on a regular or frequent basis. It's not clear to me if changing a password just for the sake of changing a password is an improvement in security, because it could lead to bad habits in terms of 1, 2, and 3. If you're asked to change your password every day, eventually you're going to reuse a password. We only have so much creativity, or if it's a randomized password each time, it's going to lead to the sticky note issue or having to use a password manager to keep track of that password. So there isn't one guaranteed approach to prevent password cracking. But in terms of now what we know about it, and now we know common approaches, think of it in terms of how hard can I make the task for my adversary? How hard can I make the task of running a password cracking software? And that is pretty much, can I make them rely just on brute force? And we can run the numbers on that in terms of how many computer years, decades, centuries, millennia are required to crack your password. And best, faith effort is good enough with regards to that. So while I hate doing this, my goal is to kind of switch to our next topic as well. Do we need a break? Do we need to kind of stretch and wake up a little bit? Okay, that was a single yes. Maybe later in the semester we'll stand up and scream instead as opposed to stretching. I just need some way to switch between topics that isn't terribly awkward. I don't like doing it, but I wouldn't want to end class already anyway. The next topic, and maybe we'll just do our introduction for it now, is that of web applications. And what's kind of interesting about this topic is that it is really just a special case of what we've already been discussing. It's a necessary topic, and we'll talk about why, but a web application is just a piece of software, right? A web application is a special type of software, and it's a special type of software that requires sort of networking functionality. So one could argue that there is no difference between web application security and software security. And semantically, I think they would be correct, right? That yes, it is just a special case of software security. The counter argument, and I think the one that wins the day, and why it's a separate topic in terms of certified ethical hacker and the type of material we're expected to cover in this course, is a couple things. One is sort of the importance of web applications as just a special class of applications. And I would say the ubiquity of web applications in the sense that you may not realize it, but effectively everything you use is a web application today, whether it appears to be one or not as you are using it. And then also some of the vulnerability classes tend to be specific to web applications. So it's an opportunity to introduce those classes and those common weaknesses in the context of web applications. This is also a little bit of a dry topic, and I'll try to do my best with it, because it is just talking more about software security without that much diving into the actual software itself. We've been doing that a little bit already in the lab. We'll be doing more of that in the lab. This is my attempt to put together a high-level architecture for a web application with a massive caveat there that is an area of like active innovation and study, right? How does one build an appropriate web application? There's no one structure of the underlying architecture for a web application. Some things are in common. There's always going to be some sort of client device. That's your web browser, that's your phone app, that's your local bundled web application here. And then there's going to be some front-end server that's almost always going to be the case. I am going to Instagram, I open up the app, I am a client that is effectively a web browser, whether it looks like it is or not, and I'm going to connect to that server that is effectively a web server, whether it looks like it's a web server or not. What then happens after the fact really depends, and there could be a lot more complexity, there could be a lot less complexity, but generally, for any sort of quote-unquote interesting web application, there is a separation between the server that's handling the basic requests and responses and the actual sort of back end and or business logic. You can think of it as the one that's actually doing the math, that's doing the interesting algorithms that are recommending things to you or applying your preferences in a specific way. That's referred to, depending on the context, as our back end, our application servers, our business logic. And then there's usually some sort of separate storage associated with that as well. That's your cloud storage, that's your data warehouse. The actual naming and the structure really does depend on the specific application. This was my attempt to make it kind of as general as possible. But what is pretty common is that between that client device and at least that front end, we're speaking a common, at least, class of languages, if not a particular languages. And this is effectively all what we refer to as just web traffic here. Whether it's actual just HTTP requests, if it's more advanced versions of that, whether we're just requesting web pages or style information or just local logic to be running, or if in many of these cases, we're just passing API calls over this format, we are using some semblance of this type of pipe to go from our local application, our client device, and the front end of the web server here. And then what is then happening on the back end really does depend. It could also be using that kind of syntax. It could be something more custom. There are a dozen popular different web frameworks, and they all kind of make different design decisions there. So I think that's enough caveat that this does not represent every scenario, and it's a highly simplified generalized view. What is important is that when we're talking about web security, web application security, we're referring to several different things of kind of equal importance. And the first is that we are actually referring to the security of this particular front end itself. We talked about how, by its very nature, if you want to be able to provide this public service, you are publicly accessible. You can't just turn it off. You can't just unplug it, right? And in this case, this is meant to be a highly available, highly accessible, high throughput interface to your web application. And so while the issues there are not necessarily unique, it's a server or a collection of servers. We learn this via the same methodology information about it. We discover vulnerabilities about it. It's still there. It's part of the web application stack. It's part of our concern with regards to web application security. There is then the actual quote-unquote application security itself. And I'm encapsulating a lot when I say that, but the nature of what is happening with regards to those requests and those responses tends to, in practice, have sort of special cases of vulnerabilities associated with them. Again, you could argue that in our OSI model or a TCP/IP view of the world, that this is all application layer traffic. It's all effectively HTTP style traffic. And so there isn't anything unique there. That is just, it's web traffic, and we've already studied issues that can happen at the application layer. And that is true. It just turns out that in practice, there have been enough interesting things discovered about this style of traffic happening at this layer. And because it is effectively ubiquitous, this requirement to have support for this type of traffic, that we can look at those, look at the common vulnerabilities that are in practice quite a bit different than race conditions with memory mapping and memory advising with copy on write semantics. And so it's worth it as a separate topic. What is also then ultimately a separate topic is the specific language and features and functionality in terms of our database storage. And we will talk about that a little bit. The main issue with that is, you really do need to gain eventually some appreciation for database and database syntax and underlying architecture and storage. And we don't do that in this class. So we'll touch on it. And there's classes you get to take if you want to learn more about databases, and then you can then choose to circle back to looking at database security. It is important, it is relevant, it's almost a whole separate topic to cover from just web application security. We'll touch upon it, and we'll do it in that kind of hand-wavy way where I'll tell you it's important and it's relevant, but we don't go into the underlying technical details of it. That's our introduction to this topic. Let's leave it just here for today, and we'll pick up right here on Tuesday. Thanks.